Hi everyone, today we're going to talk about topic 6.6 and continue our conversation of enthalpy of reactions. So as a reminder, enthalpy, or delta H, this is an extensive property of a substance. What I mean by that is it of course depends on the amount of matter. By definition, it is how much heat is transferred per mole of substance. And so it has the units kilojoules per mole, right? Because heat is measured in kilojoules. Now, if delta H is negative, this is an exothermic reaction, and it releases heat. And the exact opposite, if delta H is negative, is positive, this is an endothermic reaction, and it will absorb heat. Now, one helpful thing you can do when you're trying to calculate values using enthalpy is the following. And so let's say we have this reaction here, nitrogen gas plus oxygen gas react together to make two nitrogen monoxide molecules. And we're told this has a delta H of reaction of positive 180 kilojoules per mole of reaction. Another way you can write this to help you out is to think of it like this: N2 of gas plus O2 gas plus 180 kilojoules. Sorry, let me rewrite that. 180 kilojoules of energy is going to make 2NO gas. Essentially, this is saying that the heat is a stoichiometric part of the reaction. The heat is a stoichiometric factor of the reaction. And it'll be a little bit easier to see how to calculate things from this. And so let's say we're given this question. How much heat, otherwise known as Q, is required to react 2.4 moles of N2 with excess O2 to form NO gas, right? And so what we're looking for here is our parameter Q, and we know we have 2.4 moles of N2. And so if we're going to set this up in a kind of dimensional analysis format, we can say that we have 2.40, or just 2.4 moles of N2 per reaction. For every 1 mole of N2 that I consume, I need 180 kilojoules of energy, which is what this is saying when it's on the left side of the reaction. So I can say I need 180 kilojoules of energy. And here our moles and our moles cancel out. We should have our answer in kilojoules, which is 432 kilojoules, or in the correct number of sig figs, 430 kilojoules. And so if we add the heat as a stoichiometric coefficient here, it can help us kind of visualize some of these things. Now, a follow-up question, if we're asked if 25 kilojoules of heat was absorbed in the reaction, how many moles of NO are produced? And so we're given the 25 kilojoules. This is our heat, right? Kilojoules always mean heat. If it's kilojoules per mole, it's enthalpy. So here we have our heat, and we're looking for moles of NO. And again, we just need to look at this equation here, right? Heat is on our left side, moles of NO is on our right side. And so just like any other stoichiometric reaction, we can convert between the two. And so we can say we have 25 kilojoules of heat. In the reaction, we require 180 kilojoules. And if you react 180 kilojoules, you get 2 moles. And so it's 2 moles per 180 kilojoules. Again, the units will cancel out, and we get 0.28 moles of NO. And so this goes to show that just like our stoichiometric coefficients in front of all of our numbers here, you can use the heat stoichiometrically as well, and that's another factor into thinking about how reactions progress and how we can predict how a reaction is going to go. We'll do a little bit more practice in class, but for now, that's all. Thanks, guys.